Alright, well this is the last presentation in our module on the conceptual ideas that surround the derivative. Once this module is finished, of course, these concepts aren't going to go away, they will stay with us, and we want to be able to use them competently as we proceed and as we then use formulas, use differentiation formulas to analyze more complicated functions. But this is a very good stage to internalize the concept of curvature, to talk about curve sketching for a first time, which some people may say is a rather old-fashioned topic, but it is a good topic to teach visualization skills, sketching skills, being able to sketch curves by hand, as well as mental organization. So even if some people might poo-poo the idea of, oh my god, curve sketching by hand, you can do that with a computer. Yes, I can do that with a computer. I can also drive to my mailbox, and yet I walk. In fact, I work out to try to make sure that this aging body doesn't get any kind of trouble with heart disease and so on. So just because something can be done by a machine for us doesn't necessarily mean we have to make the machine do it. And in some cases, like I said in one of the earlier presentations, it can be downright hazardous, right? Because not enough exercise leads to all sorts of problems that we wouldn't have otherwise. Okay, well, let's take a look at higher derivatives. Sermon ends, lecture starts. Let's see, higher derivatives. Well, the first question again always is, why do we need higher derivatives? And basically, just because we know that a function is decreasing, for example, that doesn't mean that we really know the behavior of the function. For example, here we've got a set of axes, point A, point B, and say we've got a function that decreases over the interval from A to B from this point up here to this point up here. Well, it could be that the function decreases like this, or it could be that the function decreases like this. Now, this is a subtle difference in behavior, but for example, if you were in the stock market and stocks are currently going down, well, sometimes that's a good time to buy stocks, and of course, not being able to predict the future, and I'm not going to give you stock advice here, but of course the best time to buy a stock is at its lowest point. But if people offer you two stocks and one of them has past performance like this and the other one has past performance like that, well then this one here looks like it's going to break its fall earlier than the other one. Now that's no guarantee that that's going to happen in the future, but it is a way to analyze the trend of the function's behavior. So there is more than just increasing or decreasing in the behavior of a function. And of course, functions could also act rather crazily and just wiggle around like that. See, this thing is formally decreasing all the way through, but it wiggles quite a bit. The other thing is that velocities can change just like positions, and the rate of change of the velocity is the acceleration, as we've also seen in a prior presentation already. And so that's a derivative of a derivative. That's a higher derivative. Higher order derivatives then ultimately can also be used to approximate fairly complicated functions, actually, with polynomials, so-called Taylor polynomials, and we'll have a separate presentation on that a good bit later in the course. Okay, so the definition is if f is a function whose derivative is differentiable too, then we'll call f twice differentiable, and we'll denote f double prime to be just the derivative of the derivative. And in general, if f is n times differentiable, so if you can take the derivative and then the derivative and then the derivative and so on n times, and the nth derivative is that, then f is fn essentially. Then f is called n plus 1 times differentiable if and only if the n plus first derivative, which is the derivative of the nth derivative, if that thing exists. Okay, now that's horribly abstract, and of course we also want to toss some notation in here just to make sure that we don't get caught cold by that. The notation for the nth derivative is dnf over dxn. So those really aren't, it's not d to the n, it's just dnf over dxn. And it's also sometimes called fnx, so it's also not f2 to the n, it's just fn. These derivatives are related to the concept of curvature, as I neglected to mention on the first panel. And so first, let's take a look at curvature one more time and then do the abstract definition. Take a car race. We plot distance over time. We've got two cars that try to get to the finish line, which is at this coordinate here. Of course, it's a straight line race, and this is a time axis, but the finish line is at this location. Currently, both cars are here. The position data for car 1 over the beginning of the race is this. The position data of car 2 over the beginning of the race is this. Which car do you think will win? Well, car number 1 has started out fast, but the speed seems to be dropping off, whereas car 2 started a little bit slower, and it seems to be speeding up right now, or it seems to still continue to speed up. And so, based on this data, I would say that car 2 probably has a better chance to reach the finish line before car 1 than the other way around. Again, calculus is in the business of analyzing data, and then we can take some common sense or so to try to use that data to predict the future. But of course, there are all sorts of things that could still happen to these cars between here and the finish line. It's just based on the data that is available up to this point. Car 2 is probably the better prediction here as the winner. Okay, so how does that connect to higher derivatives? A twice differentiable function is called concave up if and only if the second derivative is greater than 0 for all x in the interval ab. Well, that sounds kind of strange, but let's see. The second derivative is the slope of the first derivative. And so basically, if the slope of the first derivative is positive, that means that the first derivative is increasing, and that means that your tangent lines are tilting up. So that is something that is called concave up. And it is called concave down if and only if the second derivative is smaller than 0 for all x in AB. And so basically, again, this is another one of those shadow boxing kind of things. If your derivative gives you your slopes and the second derivative is negative, that means that your slopes are declining. So that means your function tilts down like that, and that's concave down a shape. If you want to be able to memorize that, well, it's just like physics has certain kinds of right-hand rules. Basically, concave down is what you get when you just put your hand out with the palm down. Your natural curve of your hand gives you something that's concave down. And concave up is when you put your hand out the other way. The natural curve of your hand gives you something that is concave up. Okay, now the interesting thing is that even though the language suggests up and down being connected with increasing or decreasing, all combinations actually can occur. So before we go to that, let's also just quickly establish that a point where the function changes from concave down to concave up or vice versa, we call that an inflection point. An inflection point will occur where the second derivative is 0 or undefined. Now, as I said before, the combinations of growth behavior, there are 4 possible combinations, and they're all possible. So you've got growth behavior, there are 2 possibilities, increasing, decreasing, and for concavity, we have concave up and concave down. Well, what does increasing concave up look like? It has to be increasing, and the slopes have to get steeper. So it's got to be something that looks like this. Decreasing concave up has to be something that goes from a higher point to a lower point, but concave up means that your slopes are getting more positive here. So this is something that is breaking its fall. And of course, I didn't remember that I first wanted to go to increasing concave down. Okay, increasing concave down, it goes from the bottom to the top, and now our slopes are just losing speed here, if you will. Decreasing concave down, as I mentioned, it's decreasing, and our slopes are becoming more positive. So that's decreasing concave up, sorry. And decreasing concave down is something that is decreasing, and the slopes are getting more negative, and therefore things are dropping off even worse than that. Okay, well, so these are all 4 possible combinations, so don't automatically associate concave up with increasing. Concave up can also be decreasing, and don't associate concave down automatically with decreasing. Concave down can also be connected with increasing. Now we're actually coming to curve sketching, and the information that I'm going to give you below is information that we will ultimately be able to compute from the symbolic equation of the function using differentiation formulas. But here we just want to focus on the sketching process from the data itself. So let's look at the data. Function is supposed to be greater than 0 on the interval negative, the derivative is supposed to be greater than 0 on the interval -1, 1, and on the interval 3, infinity. The derivative is supposed to be smaller than 0 everywhere else. The second derivative is supposed to be greater than 0 on -infinity, 0, and on 2, infinity. And it's supposed to be smaller than 0 everywhere else. And I'm implicitly assuming here that where I'm not giving the derivative is supposed to be 0. The value at -1 is 1, the value at 0 is 3/2, the value at 1 is 2, the value at 2 is 1/2, value at 3 is -1. The limit as x goes to infinity of the function is infinity, and the limit as x goes to -infinity of the function is infinity too. Well, how do you put all that data together into a picture? This looks horribly complicated, and well, it may not be horribly complicated, but it certainly is a rather complex problem. It's a lot of data, and here's where what I mentioned before comes into play. We need to find a way to analyze this data in a very organized fashion to end up with a nice picture. And to do that, we first look at the growth behavior. So let's draw ourselves a line, and let's analyze what the derivative does. And we know and then translate that into what the function does. So we know the derivative changes its behavior at -1, and at 3. At -1, at 1, and at 3. See, -1, 1, and 3. And we know the derivative is negative here, coming from this line. The derivative is positive between -1 and 1. So that comes from here. The derivative is negative from 1 to 3. And the derivative is positive from 3 to infinity. So that's just data transcription. We just turn this into graphical information. And of course, for the function, that means the function is decreasing, increasing, decreasing, and increasing. We can do the same thing for concavity. Draw ourselves a line. We want to look at the second derivative and what that information means for the function. We know concavity changes at 0 and at 2, so we get ourselves 2 cut points, 0 and 2. And we know the second derivative is greater than 0 from -infinity to 0, so it's positive here. It's negative on 0, 2, so it's negative here. And it is positive from 2 to infinity, which gives us pluses here. And that means that the function is concave up, concave down, and concave up. Okay, so that just gives us a little bit more information. We also want to just plot the points, so we just start setting up a set of axes. And of course, now that we have some information available on the changes in behavior as well as some points, we want to scale the axes so that we hit exactly the points where things are interesting, -1, 1, 2, and 3. And on the y-axis, we just go with the scale that is given by this stuff. We should go from -1 to 2. So we get -1, 1, 2, and 3. Whoop. And notice that throughout all this, and this is probably what I should have said at the beginning, but what you want to do is you want to make sure that all these axes have the same scale, because in this fashion it'll be very easy to project this behavior up to the top axis. Okay, first of all now, even though plotting points certainly is something that computers are better at, these points here all coincide with points that we typically want to investigate, namely points where concavity or growth behavior change. So those are points that we definitely want to plot even in a hand sketch. And if f of -1 is 1, well, then we get a point here. If f of 0 is 3/2, we get a point here. If f of 1 is 2, we get another point right there. And so on. F of 2 is 1/2, and f of 3 is -1. And then we also know that the function comes from high up, from infinity, and goes back to infinity also. Okay, now, because the behavior, the growth behavior or the concavity changes at these 5 places here, basically our axis is cut up into 6 regions, cut up by these 5 places. So we just put dotted lines up, 5 dotted lines through the points where things are changing. And now we know in this region the function is decreasing concave up, which is this kind of shape. In this region the function is increasing concave up, which is this shape. In this region the function is increasing concave down, which is this kind of shape. In this region the function is decreasing concave down, which is this shape. In this region here the function is decreasing concave up, which is this kind of shape. And here finally the function is increasing concave up, which is this shape. And now basically you could say that these are shapes for railroad ties that just have to go through these points and connect these points. And so now we can just start sketching, and the function basically becomes concave, decreasing concave up, comes in like this, changes to increasing concave up, then to increasing concave down, then to decreasing concave down, to decreasing concave up, and finally to increasing concave up, and that would be how we would sketch this graph. Now, we will see in a presentation where we do this for a function that is given symbolically that these graphs are surprisingly exact, and of course they also train, aside from the mental organization and the making connections between symbolic stuff, the pluses and minuses here, and the graphical connection, then connecting these graphics to each other. Aside from that, it also trains the organization, as I mentioned, and it also trains, as we sketch this graph, it trains some manual dexterity, and that is very important also in scientific face-to-face communication, because oftentimes you just want to show a picture as to how something looks, and it may just be easier to draw the picture than to describe something in words there. Okay, with that, we're finally finishing out with another result that is useful in determining where a function has maxima or minima. It's called the second derivative test. And, well, basically you've got a function. You want it to be twice differentiable now in a little interval. And remember, that looks so horribly technical, but it just means that there's a little bit of wiggle room around a from a minus delta to a plus delta. We want that the second derivative is continuous in this interval, and the first derivative is supposed to be 0 at the point a, which is indicative that there may be a maximum or a minimum, or we have also seen it could be one of those saddle point things. If the second derivative is smaller than 0, then f has a local maximum. And if the second derivative is positive, then the function has a local minimum. That's the theorem. In our final slide, we're going to talk about how that test comes about. This is something that can be memorized, but there actually is a way to really see this conceptually, and I'll talk to you about that on the last panel. Right now, I'd like to also mention, however, that for single variable function, the second derivative test can often be replaced with an analysis of the growth behavior. If you know where the function changes from increasing to decreasing or from decreasing to increasing, you know, let's see, what is it? Increasing to decreasing is a maximum, decreasing to increasing is a minimum, and then you wouldn't have to contend with the situation that sometimes also happens here, that the second derivative is 0, in which case this test, as it's stated here, doesn't say anything, but then the test could be extended into a more complicated theorem. However, we want to keep this idea of the second derivative test around, because for multivariable functions, the higher dimensional analog of this theorem is really just about the only way to identify extrema. Okay, so the question that we could ask ourselves here is, why does the second derivative test work? So that goes along the lines of a proof, but it could also be replaced with the question, how do I remember this test? I mean, it's greater than 0 gives us what? A minimum or a maximum, and well, that's easily confused, right? So how does this go conceptually? Well, let's take a look at the second derivative. Second derivative smaller than 0 implies, well, let's see, anytime a derivative is smaller than 0, that means that the function is decreasing. So second derivative smaller than 0 means that the first derivative is decreasing, and that's something we can visualize, because the first derivative is supposed to be 0 at the point a. That was the other part in the second derivative test, and so if it's decreasing, it's got to look like this. It can do anything over here, it can do anything over here, but near a, it's going to be decreasing, and if we zoom in far enough, it may even look like approximately a straight line, because after all, we're assuming that the first derivative is differentiable again. Okay, but what does that mean? That means that f prime is greater than 0 to the left of a, and that means that the function is increasing to the left of a, and f prime is smaller than 0 to the right of a, which implies that the function is decreasing to the right of a, and that means that the function changes from increasing to decreasing, and so that means that the function has a local maximum at a. So this is, quite honestly, how I remember the second derivative test. I don't memorize it as a theorem. Anytime I need to really figure out what a positive or negative second derivative means, I just go through this spiel here one more time, either for the negative derivative or for the positive derivative. And just by having acquired this skill of visualizing things reasonably well, I get the right result and I can move on. Now, this may feel a little convoluted, and it certainly may be more efficient if you have good verbal memory to just memorize the second derivative, but I want to encourage you to really think in these kinds of concepts, think in these kinds of pictures. Remember what I said in the introductory presentation for this calculus course. one of the most important skills we're developing here is the skill to visualize. And the only way to do that is if we're doing these kinds of pictures, if we're doing this kind of shadow boxing that I've done where I had to put my face into the presentation one more time earlier on here. That's the kind of thing that really will allow you to work efficiently with these kinds of concepts, just like the practicing of algebra will allow you to work efficiently with algebra. All right, now you've probably been waiting for it for quite a while, and in the next presentation we're going to start deriving differentiation formulas, which will then allow us to connect these concepts with all sorts of symbolic functions. Thank you very much.